So let's have a look at the second set of graphs. Both of these happen to be logarithm graphs. And just as a reminder, log graphs in general look like this. Depending on your base, looks like our base here is going to change things up a bit in number 4. So for number 3, log base 2x minus 1 plus 3. Once again, as we've seen before, this 3 out here and this 1 out here will have a property of shifting up 3 and 1 to the right, all points we find for the parent graph, which would be y equals log base 2 of x. So my first job would be then to set up a little t-table, x, y, and grab a few points from the log base 2 of x. And again, if I rewrite that in exponential form to make my life a little easier, I can actually get some points on this log graph this way. I can select the y's first, some classic values, and figure out the x values. 1, 2, 4, and negative 1 power on the 2 would generate a 1/2 answer. So there's a few points for me to work on the log base 2 graph. So now as we start to plot these points, 1 across, 0 up puts us here. A y value of negative 1 puts me at 1/2. Try to get a dot there about halfway. 2 over 1 up. And 4 over 2 up puts us here. So now those points are the parent graph for log base 2 of x. I'm going to go to green for my new ones. So now my shifts happen to each of these points, and the green graph will be my final graph. I need to go 3 up from each point and 1 over. 1, 2, 3. So this point will be here. I'll do that fractional point last. This point will be up 3 and over 1. And my fourth point will be up 3 and over 1. And lastly, to try to pull this half point in, that'll occur right about here. So my curve is looking something like this. And notice that the x minus 1 has shifted my vertical asymptote to positive 1. This all helps me pull together my range and my domain. It looks like my domain here is all real numbers such that x is greater than 1. And my range here is all real numbers. So notice from the exponentials, the domains and range have essentially somewhat shifted roles, and the x's have become the y's, and the y's have become the x's. And this is kind of typical behavior for inverses, which we mentioned. Log graphs are inverses of exponentials where you flip-flop the y and the x. So this might be in green down here, your standard exponential style. And the inverse, of course, is there in blue, which is simply a rewrite of the log graph. Again, log graphs are inverses of exponentials. All right, let's get our second guy. Here we have a log base 1/2, and your job is to figure out what will the plus 1 over here do to that graph. It will, of course, shift it 1 unit this way. There is no vertical change here, but this will change the asymptote again. So all we have to do then is make a short t-table, x, y for this graph, and again to help us out, 1/2 to the y equals x is our rewrite. So let's look at what happens as we choose a few y's first here. 0, 1, 2, negative 1, negative 2, just to look at a couple of values. If the y is 0, of course, x is 1. If y is 1, we have a value of 1/2. And if y is 2, we have a value of 1/4. A negative 1 will generate a 2, and a negative 2 will generate a 4. This, again, is the graph of y equals log 1/2 x, and we did that as the rewritten form to make our life a little easier. So plotting points, 1 across, 0 up puts us right here. 1/2 across and 1 up puts us here. 1/4 across and 2 up puts us here. We're getting closer to that vertical line. Not hitting it though. A y of negative 1 puts us at 2, and a y of negative 2 puts us at 4. So we're seeing our curve show up here as we start to generate it. Notice you will have a vertical asymptote at the y-axis again. And now we employ our changes. I will shift to green, and we simply shift everything we have sideways 1. So I'll start here with the easy to locate point. Here's our second, and here's our third, and now we'll grab these other values here. It's about halfway, it's about a quarter of the way. So our curve then is taking shape. And as we carefully bring it up here, we also want to include our new vertical asymptote at y equals negative 1, which will help us then write the domain and range. Now let's look at the domain first. It looks like I have values on my green graph everywhere to the right of my dashed red line. So that would mean all real numbers such that x is greater than negative 1. And the range vertically scanning up and down on my graph, I can see I will hit all possible values if I'm patient enough and I wait long enough as my graph here continues to the right. Put arrows on the ends to clean things up. And we look all right. And now let's proceed with some of these here. Again, properties of exponents apply. Here, since we have multiplication, we simply add the powers. So that's a pretty straightforward answer. Once again, number 6, we're adding powers. Number 7 is an example of multiplication of powers. This is the power of a power property. For number 8, we have division, which requires subtraction of exponents as long as the bases match, which they do. And again, the base can be this natural constant e. For number 9, the numbers in front, the coefficients, multiply as normal, and the exponents then add, but we don't want to leave negative exponents in the answer. So 20 over e to the 4th would be an appropriate fix for this first value. For number 10, this 3 basically gets distributed to each component inside as long as there's multiplication happening, and that gives us a final answer of 8e cubed. For number 11, with the coefficients, we are simply dividing. That will leave a 1 on top and 8 underneath. And for the exponents, we subtract. Since we have a positive value, that will be our final answer. For number 12, e in the original has a first power. So essentially, we are subtracting those powers. And when we have e to the 1 minus x plus 1 power, it'll be 1 minus x minus 1, leaving e to the negative x. And again, we do not want to leave that as a power. So let's write 1 over e to the x for problem 12.